You don't begin with a theory. You begin with a shape, a curve traced across the sky so large that even saying its size feels wrong. A structure measured not in thousands or millions of light years, but in billions, wide enough that light itself would need more than 1 billion years just to cross it. Not a cluster, not a wall, a ring-like arc, suspended in deep cosmic time, appearing where smoothness was supposed to reign. This is not the kind of discovery that explodes. It unsettles. Because according to everything modern cosmology teaches, the universe is allowed to be lumpy only up to a point. Galaxies gather into clusters. Clusters stretch into filaments. Filaments weave a vast cosmic web. But beyond a certain scale, all of that texture should fade. The universe should blur. Matter should average out. Patterns should dissolve into statistical calm. And yet, here is a ring, not small, not local. A structure so extended that it appears to ignore the rulebook entirely. Before going further, pause for a moment. If this kind of question is why you watch videos like this, if you're drawn to the places where certainty starts to crack, consider subscribing, not for answers, but for the habit of asking better questions. And if you already have an instinct about this ring, real or illusion, hold on to it. We'll return to it later. For now, just stay with the discomfort. The reported structure sits billions of light years away, meaning it formed when the universe was less than half its current age. At that time, matter was still settling into the scaffolding laid down by the Big Bang. The cosmic web was younger, more chaotic, less refined. And yet the pattern appears coherent, stretched, continuous, improbably organized. If this structure is real, it doesn't just add a new object to a catalogue. It challenges the idea that the universe becomes uniform when viewed from far enough away. That idea has a name: the cosmological principle. It's not a law of nature written into the fabric of space-time. It's an assumption carefully tested, repeatedly supported, that says the universe, on the largest scales, looks statistically the same in every direction. No preferred locations, no special edges, no giant fingerprints. This ring looks like a fingerprint. But here's the twist that makes this story dangerous. You are not looking at the universe directly. You are looking at data, shadows of distant objects, absorption lines imprinted on quasar light, catalogues compiled by surveys that scan some parts of the sky better than others, distances inferred from redshifts, structures reconstructed from probabilities. In other words, the ring exists first as a claim, not as an object you can point a telescope at and photograph. That distinction matters, because the universe has a long history of appearing to break its own rules until better measurements showed that it didn't. The canals of Mars, the steady-state universe, faster than light neutrinos. Each time, the anomaly felt profound. Each time, humility eventually followed. And yet, anomalies are not mistakes by default. Every genuine breakthrough once looked like a violation. The expansion of the universe, dark energy, the cosmic microwave background itself. Progress does not come from ignoring uncomfortable data. It comes from interrogating it relentlessly. So the question is not simply, is the ring real? The deeper question is, what does real mean when you're mapping something this large? Imagine standing inside a fog so thick you can barely see 10 meters ahead. Now imagine trying to map the entire landscape by listening to echoes. Some patterns will emerge. Some will be artifacts of how and where you shouted. Others might reflect real cliffs and valleys. From inside the fog, the difference is not obvious. Cosmology works in a similar way. We infer the large-scale structure of the universe by tracing how matter absorbs light, how galaxies cluster, how statistics behave when samples get enormous. When you sift through enough data, Patterns will always appear. The challenge is knowing which ones mean something. That's what makes this ring unsettling rather than triumphant. Its scale is uncomfortably close to the limit beyond which structure should not remain coherent. Large-scale simulations of the universe built from gravity, dark matter, and the expansion of space rarely produce features this extended without breaking into smaller, disconnected pieces. To see something that looks continuous at this size is like seeing a ripple on the surface of a perfectly calm ocean that stretches from horizon to horizon. Your instinct might be to ask, why hasn't this rewritten cosmology already? The answer is simple and unsatisfying. Because extraordinary claims do not collapse under their own weight, they are dismantled slowly, from multiple angles, by skepticism that is just as rigorous as curiosity. And skepticism cuts both ways. If the ring is real, it would suggest that the universe retained large-scale correlations far longer than expected, that the early cosmos imprinted structure more strongly than our models predict, that the assumption of smoothness, while useful, may be incomplete. If the ring is not real, then it becomes a lesson about how easily meaning can emerge from noise when datasets grow vast and human intuition remains unchanged. Both possibilities are profound. Notice something important here. There is no villain, no conspiracy, no failure. This is not a story about science being wrong. It's a story about science doing what it's designed to do. Press against its own boundaries until they either hold or crack. And at this moment, the boundary is quiet. The ring has not vanished. It has not been universally confirmed. It sits in a gray zone, where evidence is suggestive but not decisive, where some analyses find coherence and others find statistical fragility, where the shape seems compelling until you rotate the data, change the selection criteria, or ask whether you noticed it only because you were looking for something unusual. This is where cosmology becomes less like exploration and more like self-examination. How confident should you be in a pattern that appears only after millions of data points are filtered, weighted, and interpreted? At what point does skepticism turn into denial? And at what point does excitement turn into self-deception? These are not technical questions. They are human ones. You live in a universe so large that you will never see more than a thin slice of it. Everything you know about its grandest structures comes from inference, layered upon inference. That doesn't make the knowledge meaningless, but it does make certainty rare. The ring hangs there, suspended between two stories. One in which the universe is stranger than expected, and one in which your tools and instincts conspired to mislead you. For now, neither story has won. You are left with a shape hanging in the dark, not dramatic, not explosive, just quietly wrong. In a universe built on averages, this ring refuses to blend in. And once you've seen it, the silence around it feels heavier than any answer. Size is supposed to comfort you. At small scales, the universe is chaotic. Stars explode, galaxies collide, matter clumps, stretches, tears, and reforms. But as you zoom out far enough, cosmology promises the mess should smooth itself away, like noise fading into silence, like ripples dissolving into a flat sea. This expectation is not aesthetic, it is structural. Modern cosmology rests on a quiet assumption that beyond a certain scale, the universe stops favoring any direction or location. It doesn't mean everything is evenly spaced. It means irregularities cancel out when viewed from far enough away. Peaks balance valleys. Clumps dissolve into averages. This is where size stops being impressive and starts being dangerous. Because the moment a structure appears too large to be averaged away, it doesn't just add detail. It challenges the framework that lets cosmologists turn observations into laws. To understand why, you have to let go of the idea that cosmology is about objects. It's about statistics, Galaxies are not studied one by one. They are counted, grouped, correlated. Their positions are turned into probability fields. Their separations become distributions. At large scales, the universe is not described as a place, it's described as a set of expectations. And those expectations say this: structure has a limit. Below that limit, gravity dominates. Matter flows along filaments of dark matter. Clusters grow. Walls stretch. Voids expand. But above that limit, expansion wins. The universe becomes indifferent to detail. No direction should look special. No pattern should persist coherently across billions of light years. This isn't philosophy. It's math tested against observation. So when a structure approaches that boundary, when its scale rivals or exceeds the length at which homogeneity is expected, size itself becomes the anomaly. At that point, the question is no longer, how did this form? It becomes, are we interpreting what we're seeing correctly? Because the universe does not hand you scale directly. You reconstruct it. Distances are inferred from redshift. Redshift depends on expansion, which depends on cosmological parameters. Those parameters are measured statistically, not locally. Every step assumes the previous step behaves the way the model predicts. If a structure violates the model at its core assumption smoothness, then every inferred distance inside that structure becomes suspect. The map starts questioning the ruler. This is why cosmologists grow uneasy around phrases like the largest structure ever discovered. Quick, large compared to what? Discovered using which method? Measured under which assumptions? There is a subtle but crucial difference between big and too coherent. The universe is allowed to have large things. Superclusters span hundreds of millions of light years. Filaments connect them across vast distances. Even walls stretching over 1 billion light years have been catalogued and studied. What unsettles cosmologists is not sheer size, it's organization at scale. A randomly shaped overdensity can be dismissed as cosmic variance, the natural randomness expected in any large system. But a coherent arc, a ring-like alignment, a pattern that suggests geometry rather than chaos, those demand explanation. Patterns imply memory. Memory implies cause. And at these scales, known causes are limited. Gravity alone struggles to maintain such coordination over billions of light years without fragmentation. Dark matter smooths, but does not sculpt shapes deliberately. Expansion pulls everything apart. The early universe imprinted fluctuations, but those fluctuations are expected to be statistically random beyond certain lengths. So when size crosses from large into organized and large, the universe starts behaving less like a fluid and more like a message. And messages make scientists nervous. But there is another side to this discomfort. The human brain is exquisitely tuned to detect structure. Evolution rewarded pattern recognition because it kept you alive. Seeing shapes where none exist was safer than missing a predator hiding in tall grass. That instinct did not evolve for billion light-year datasets. When cosmologists sift through enormous surveys, millions of data points, thousands of parameters, patterns are not rare. They are inevitable. The danger lies in mistaking inevitability for significance. This is where size becomes seductive. A small pattern can be ignored. A medium one can be debated. A massive one demands attention simply because it feels consequential. But magnitude alone does not guarantee meaning. If you search long enough, you will always find something extreme. That's not cynicism. It's probability. Imagine throwing darts at a wall blindly for hours. Eventually, a cluster will form that looks intentional. The cluster didn't arise because of aim. It arose because you kept throwing. In cosmology, the wall is the sky. The darts are data points. The longer and deeper the survey, the more likely it is that something unusual will emerge.
This repetition,
this does not make discoveries invalid.
The cosmological
it makes skepticism essential. So when size becomes a problem, The real issue is not whether the universe is broken. It's whether your expectations are calibrated correctly. Do you expect smoothness everywhere, or statistical smoothness on average? Do you expect no large structures, or no persistent correlations at extreme scales? Do you expect patterns never to appear, or to appear occasionally, by chance alone? These distinctions sound technical. They aren't. They determine whether a structure forces a rewrite of cosmology or quietly dissolves under reanalysis. And here's the uncomfortable truth. You often cannot tell which outcome is correct at first glance. Science does not reward shock. It rewards patience. That patience can feel anticlimactic. It can feel like hesitation in the face of wonder. But without it, cosmology would collapse under the weight of its own excitement. So when size becomes a problem, it's not because the universe has done something forbidden. It's because the universe has pushed you into a regime where intuition fails, where large is no longer a descriptor, it's a test of assumptions, a test of methods, a test of humility. You are not standing outside the universe, measuring it cleanly. You are embedded within it, reconstructing it from fragments of light that have traveled for billions of years before touching your instruments. At that scale, error is not a flaw, it is the default. The real question, then, is not whether the universe allows something this big. It is whether you know how to tell when bigness means something and when it doesn't. Bigness alone is easy to announce. Understanding what it implies is harder, and somewhere in that difficulty, cosmology reveals what it truly is, not a catalogue of objects, but a discipline built to resist being fooled by scale. Bigness stops being impressive the moment it starts breaking rules. At that scale, awe gives way to discomfort, because now the universe isn't just large. It's behaving in ways that demand explanation. Distance feels simple when you live on a planet. You step outside, look at the horizon, and your brain does the rest. Near things feel close. Far things feel distant. Perspective shrinks mountains, stretches roads, compresses cities into skylines. Even when you're wrong by an amount that barely matters. The universe offers no such mercy. In space, distance is not something you see. It is something you reconstruct indirectly, cautiously, and never all at once. Every measurement is a translation. Every number is a compromise between what light tells you and what theory allows you to assume. That's the first lesson of cosmology. The universe does not come with a ruler. Start with the most basic problem. How far away is a star? You cannot walk toward it. You cannot send a tape measure. You cannot wait for an echo. All you receive is light photons that left long before you ever existed, carrying no label that says where they came from. So you cheat. You move your viewpoint and watch how the star appears to shift against a more distant background. A tiny wobble. A fraction of a degree. This is parallax, the same trick your brain uses when you close one eye and then the other. For nearby stars, it works, barely. Beyond that, the wobble vanishes into noise. Distance grows faster than precision. The universe outruns your geometry, so you invent new strategies. You look for objects whose intrinsic brightness you think you understand. If you know how bright something truly is, and how dim it appears, you can infer how far it must be. This sounds clean. It isn't, because to know intrinsic brightness, you must trust models of stellar physics. You must assume stars behave the same everywhere. You must calibrate one rung of the ladder using another. Each step depends on the last. Cosmologists call this the distance ladder. And ladders are honest metaphors. They are useful, but they wobble. Remove one rung, and everything above it becomes questionable. Eventually, even brightness fails you. At extreme distances, individual stars blur into galaxies. Galaxies blur into statistical populations. And distance stops being something you assign to an object. It becomes something you infer from the expansion of space itself. This is where redshift enters the story. Light stretches as the universe expands. The farther it travels, the more its wavelength is pulled toward red. Measure that stretching, and you can estimate how much the universe has expanded since the light was emitted. That estimate gives you distance, but only if you already know how fast the universe expands. And that expansion rate is itself measured using distances. The universe closes in on itself like a hall of mirrors. At small scales, these uncertainties are manageable. Errors cancel, patterns survive. But as you push outward toward billions of light years, uncertainty compounds. Each assumption echoes into the next. This is the regime where the ring appears, a structure so large that its very existence depends on how confidently you believe your distances. Shift them slightly. Change the model parameters. Adjust the statistical treatment. The shape stretches, warps, fragments, or disappears. This does not mean the data is bad. It means the universe is subtle. You are not measuring a table in a room. You are reconstructing a three-dimensional history from two-dimensional shadows, filtered through cosmic expansion, detector sensitivity, and human expectation. And yet, cosmology works. That's the miracle worth pausing on. Despite these limitations, independent methods converge. Maps drawn using different tracers, galaxies, quasars. Absorption lines agree more often than they should. Simulations built from simple rules reproduce large-scale patterns with eerie accuracy. The universe, for all its vastness, behaves consistently enough to be studied at all. But consistency is not perfection. When you reach the largest scales, the margin between signal and illusion narrows. The difference between a genuine structure and a statistical artifact can hinge on how you bin data, how you define neighbors, how you correct for incomplete sky coverage. These are not cosmetic choices. They shape reality as you perceive it. Imagine trying to understand the shape of a forest by counting trees through fog from a moving train. Using binoculars that only work in certain directions, you would still learn something, but your conclusions would depend on where you looked longest, what you expected to find, and how you grouped what you saw. Cosmology is no different. This is why measuring the universe is not an act of dominance. It's an act of negotiation. Between observation and inference, between theory and humility. When a structure appears to violate expectations, the first instinct is not celebration. It is interrogation. How robust is the distance estimate? How sensitive is the pattern to selection effects? What happens if the same analysis is applied to simulated universes known to be smooth? These questions are not obstacles to wonder. They are what make wonder trustworthy. Without them, every anomaly would become a revolution, and revolutions, repeated too often, lose meaning. Learning to measure the unmeasurable teaches you something deeper than technique. It teaches restraint. It reminds you that the universe does not owe clarity to curiosity, and yet, curiosity persists. You continue measuring, because not measuring leaves you blind. You build ladders knowing they sway. You trust averages knowing they hide extremes. You accept uncertainty because the alternative is silence. The ring lives inside that tension. It is not just a question about size or structure. It is a question about how far you can push inference before it pushes back. About whether your tools are revealing a genuine scar in the cosmos or amplifying a coincidence into significance. You are not asking the universe to explain itself. You are asking whether your explanation methods are strong enough to survive discomfort. Every time cosmology advances, it does so by turning limitations into diagnostics. Errors are not discarded, they are studied. Biases are not ignored, they are modeled. Measurement becomes self-aware. This is slow. It is unglamorous. It does not trend well on headlines. but it is the only reason the universe remains intelligible at all. So when you hear about a structure that seems too large to exist, remember this: the most difficult thing to measure is not distance, it is confidence. Confidence that a pattern reflects reality. Confidence that absence is meaningful. Confidence that what you cannot see is not quietly steering what you think you understand. Every cosmic measurement is a claim made under uncertainty. Some claims survive scrutiny. Others teach you where your vision falters. Distance, in the end, is not just space between objects. It is space between what you observe and what you believe. And learning to measure the universe means learning to live inside that gap. Every number you trust is built on fragile steps, angles, shadows, assumptions, distance. It turns out, is not something you see, it's something you infer. And inference is where uncertainty quietly enters the story. Every map of the universe begins with a mistake, not an error, but a limitation, an edge beyond which human intuition fails. Long before cosmology had equations or computers, it had observers staring into the night, trying to turn pinpoints of light into a sense of depth. The first breakthrough came from a simple realization: the sky is not flat. Ancient astronomers noticed that nearby stars shift slightly against the background as Earth moves through its orbit. It was a tiny effect, almost insulting in its subtlety. But that shift parallax was the first crack in the illusion that the heavens were a painted dome. One of the earliest to formalize this idea was Hipparchus, working with naked-eye precision that feels almost impossible today. Parallax did not give humanity the universe. It gave humanity depth. For the first time, stars were not just lights. They were locations. But the method had a cruel ceiling. As distances grew, parallax angles shrank until they vanished into uncertainty. Beyond a few hundred light years, geometry surrendered. The universe refused to cooperate with triangles. Centuries passed before the next rung of the ladder appeared. In 1838, Friedrich Bessel measured the parallax of the star, 61 Cygni, a wobble so small it could barely be trusted. Yet it worked. The result wasn't just a number, it was a proof that stellar distances were measurable at all. From that moment on, astronomy shifted from cataloging lights to constructing scales. Stars became laboratories. Their brightness, color, and variability were studied until patterns emerged. Some stars pulsed with a regular rhythm, brightening and dimming like cosmic metronomes. If you knew the rhythm, you could infer the true brightness. If you knew the true brightness, you could infer distance. That insight unlocked the next dimension of the universe. When Edwin Hubble identified such variable stars in the fuzzy smudge known as Andromeda, everything changed. Andromeda was not a cloud within the Milky Way. It was a galaxy, an island universe far beyond our own. The universe did not merely expand, it multiplied. Suddenly, distance was no longer a problem of stars. It was a problem of galaxies, hundreds of billions of them, scattered across space, each one a city of suns. And as more galaxies were measured, a pattern began to appear, not in their individual properties, but in how they were arranged. They were not sprinkled randomly. They gathered, they avoided, they aligned. They left behind enormous empty regions, like bubbles blown into the fabric of space. Between those voids, matter stretched into filaments long, faint threads connecting clusters across hundreds of millions of light years. This was the first glimpse of the cosmic web. No telescope ever photographed it directly. What you see in images is reconstruction data translated into structure, statistics rendered into shape. The web is not a thing you point at. It is a pattern you infer from where galaxies prefer to exist. At this point, cosmology crossed a threshold. The universe was no longer understood as a collection of objects. It became a system, a dynamic, evolving network governed by gravity, expansion, and the invisible influence of dark matter. Dark matter does not emit light, it does not form stars, but it dominates the mass budget of the universe. Its gravity sculpted the web long before galaxies lit up. Ordinary matter flowed into its valleys, tracing outlines drawn by something unseen. This idea solved a problem that had haunted astronomers for decades. Galaxies moved too fast. Clusters held together too tightly. Something else had to be there. And when simulations included dark matter, simple particles, interacting only through gravity, the cosmic web emerged naturally. Filaments, knots, voids. A universe that looked uncannily like the one inferred from surveys. Order, born from chaos. But here is where the story loops back on itself. The cosmic web is lumpy, but statistically smooth. Filaments can stretch for hundreds of millions of light years, sometimes more. Walls can span even larger distances. Yet when you zoom out far enough, the texture fades. The universe averages itself into sameness. That averaging is not optional. It is the reason cosmology works at all. Distances, expansion rates, and ages rely on the assumption that the universe has no preferred direction at the largest scales. Without that assumption, measurements collapse into local quirks. There is no global story. So when something appears that seems too organized, too extended, too coherent, it presses directly against the boundary where the cosmic web is supposed to dissolve. The ring does not live among stars. It does not live inside galaxies. It lives at the level where the universe is meant to forget detail. That is why it feels unsettling. From parallax to galaxies, from galaxies to filaments, cosmology learned to see structure where none was obvious. But it also learned restraint. Not every alignment matters. Not every cluster signals new physics. The history of cosmic mapping is a history of resisting temptation. Every generation saw patterns it wanted to believe. Spirals mistaken for solar systems, nebulae mistaken for nearby clouds, apparent alignments that dissolved under better data. Progress came not from rejecting patterns, but from demanding they survive scrutiny. The cosmic web itself survived because it appeared everywhere, across surveys, methods, and wavelengths. It did not depend on one way of looking. It persisted. That persistence is the standard. And now the ring asks a quiet but uncomfortable question. Does it persist? Or does it evaporate when examined from another angle? This is not a failure of science. It is its rhythm. Each step outward from parallax to stars, from stars to galaxies, from galaxies to the web, expanded humanity's reach while sharpening its caution. The larger the map became, the more disciplined interpretation had to be. You did not gain certainty as the universe grew. You gained responsibility to separate structure from suggestion, to distinguish what the cosmos actually built from what your tools and instincts might have assembled for you. From parallax to the cosmic web, cosmology learned how to see, but it also learned when not to believe its first impression. What began as tiny shifts in starlight became a map of unimaginable depth. Humanity didn't conquer distance, it learned to negotiate with it, and every improvement revealed just how much more there was to miss. There is a quiet idea beneath everything you think you know about the universe. It is not flashy. It does not announce itself with equations or images. Most of the time, it is not even mentioned. And yet, without it, cosmology would fall apart into disconnected facts, interesting, precise, and meaningless when taken together. The idea is simple enough to sound harmless on the largest scales. The universe looks the same everywhere, not identical, not perfectly smooth, just statistically uniform. No favored directions, no privileged locations, no cosmic center where the rules change. This is not something the universe promised you. It is something you assumed carefully, provisionally, and because it kept working. When you measure the expansion of space, You assume that distant galaxies recede the same way in every direction. When you estimate the age of the universe, you assume the laws of physics did not quietly shift beyond your horizon. When you turn local observations into global conclusions, you assume your patch of cosmos is not special. This assumption does not simplify the universe. It makes the universe measurable. Without it, every observation becomes parochial, a local quirk mistaken for a universal truth, a regional anomaly promoted to cosmic law. The story stops scaling. That is why this assumption, so modest on the surface, holds the entire framework together. It is tested constantly, but never proven absolutely. You cannot step outside the universe to check whether it is truly the same everywhere. You can only look farther and farther away and ask whether differences fade or persist. So far, they fade. The cosmic microwave background looks nearly identical in all directions. Large surveys show the same statistical patterns repeated across the sky. Simulations built on this assumption reproduce the structures you observe with remarkable accuracy. The universe behaves as if it agrees with you, but agreement is not the same as guarantee. This is where discomfort enters, because the assumption works best when structure averages out. When clumps cancel clumps, when filaments intersect enough that no single one dominates the picture. Smoothness is not the absence of structure, it is the balance of many structures competing. Now imagine a feature so large, so coherent, that it resists being averaged away, not a dense cluster, not a filament, but something shaped, suggestive, persistent across distances where randomness should dominate. That is when the assumption stops being background noise and becomes the main character. You feel it immediately, even if you don't name it. A tightening, a sense that something foundational is being leaned on too hard. If the universe allows such coherence at extreme scales, then either your assumption has limits or your interpretation does, and the difference matters. Because cosmology is not built from certainties stacked neatly upward. It is built from assumptions that are constantly stress-tested. When they survive, they fade into invisibility. When they strain, everything, depending on them, becomes fragile. The smoothness of the universe is one of those load-bearing ideas. It does not say there are no large structures. It says there are no preferred large structures, no special shapes, no cosmic handwriting, no region that remembers the early universe better than another. When something looks like handwriting, skepticism is mandatory. But skepticism does not mean dismissal. It means asking sharper questions. Does this structure appear everywhere, or only in certain data sets? Does it survive changes in method, or only one way of slicing the data? Does it reflect the universe's behavior or the survey's geometry? These questions are not barriers to discovery. They are filters. They separate anomalies that teach from anomalies that mislead. And this is where the assumption reveals its true role. It is not a claim about reality. It is a discipline imposed on interpretation. It tells you, before you rewrite the universe, make sure the universe is the thing asking to be rewritten. The danger of violating this assumption too quickly is subtle. You do not just risk being wrong, you risk breaking the coherence that lets cosmology exist as a unified narrative. If the universe is fundamentally different in different directions, then the age of the universe becomes ambiguous. The expansion rate becomes regional. Cosmic history fragments into local stories that cannot be stitched together. The universe would still exist. Understanding it would become harder to justify. That is why the assumption persists, not out of dogma, but out of necessity. It is the minimal rule required for a global story to make sense. And yet, no assumption is sacred. History shows that when an assumption fails consistently and decisively, science adapts. Newtonian space and time once felt equally foundational. They dissolved when evidence demanded it. The same could happen here. But that transition would not come from a single image or headline. It would come from repeated, independent failures, from patterns that refuse to disappear no matter how you examine them, from coherence that survives skepticism. One anomaly is interesting. A pattern that survives doubt is transformative. The ring exists at the edge of that distinction. It presses against the assumption without clearly breaking it. It creates tension without resolution. It forces you to look again at what you quietly trusted. That tension is productive. It reminds you that cosmology is not a catalogue of objects, it is a network of expectations. And expectations must remain negotiable. You are not wrong to rely on this assumption. Without it, nothing scales. But you are also not entitled to protect it from challenge. Science advances not by loyalty, but by survival. An assumption that holds only because it is comfortable will fail eventually. An assumption that holds because it has endured scrutiny earns its place temporarily. The universe does not care what framework you prefer. It will continue expanding, clustering, and aging whether your models survive or not. Your responsibility is simpler and harder: to notice when an assumption is being tested, to resist the urge to resolve tension too quickly, to let uncertainty do its work. The smoothness of the universe has carried cosmology far. It may carry it farther still, or it may reveal seams you did not expect. Either outcome is acceptable. What is not acceptable is mistaking convenience for truth. The universe does not promise uniformity. You assume it, because so far it has been useful, and usefulness, in science, is always provisional. The assumption holds until it doesn't. Every map lies, not because it intends to deceive, but because it must choose what to include, what to ignore, where to look longer, where to stop. A map is not the territory, it is a negotiation between reality and limitation. Cosmic maps are no different. When you look at an image of the universe, dots of galaxies, filaments traced in faint light, it feels authoritative, clean, objective. But that confidence is borrowed. Behind every cosmic map is a chain of decisions that quietly shape what you think you're seeing. Telescopes do not see everything. They see what their design allows. Some parts of the sky are surveyed deeply, repeatedly, obsessively. Others are skimmed. Some wavelengths are favored because Earth's atmosphere lets them through. Others are blocked entirely. Dust obscures certain directions. Bright stars contaminate others. The Milky Way itself cuts a scar across the sky, hiding distant galaxies behind its glow. So cosmologists do what they must. They work around the gaps. They stitch together surveys taken at different times, with different instruments, for different purposes. They correct for missing regions. They weight data to compensate for uneven coverage. They simulate what should have been seen where nothing was observed. Each correction is reasonable. Each correction is necessary. And each correction adds interpretation. This is where imperfection enters not as failure, but as structure. When mapping the universe, you are not photographing an object. You are inferring a distribution. You do not see matter directly. You see tracers, galaxies, quasars, absorption lines. Each tracer is biased. Galaxies form where conditions allow. Quasars flare briefly and vanish. Gas absorbs light only under certain temperatures and densities. The map you build depends on which tracer you trust. Choose galaxies, and you trace luminous matter. Choose absorption lines, and you trace gas shaped by gravity you cannot see. Choose quasars, and you sample rare, bright beacons scattered unevenly across cosmic time. None are wrong. None are complete. Now add scale. At small distances, imperfections blur, errors average out. At enormous distances, billions of light years, the imperfections begin to align. Survey edges line up with features. Selection effects stretch into shapes. What was once noise acquires geometry. This is not speculation. It is a known hazard. Imagine painting a mural while wearing glasses that only sharpen certain colors. Over time, patterns will emerge not because the wall demanded them, but because your vision favored them. Step back far enough, and the distortion becomes the dominant feature. Cosmic surveys face the same risk. This is why cosmologists obsess over selection functions, mathematical descriptions of what a survey could have seen if the universe cooperated perfectly. It is why mock universes are generated by the thousands, run through the same pipelines, distorted by the same blind spots, and compared against reality, not to prove reality is fake, but to prove that interpretation is fragile. The ring sits exactly where fragility matters most. It appears near the boundary of survey coverage. It relies on traces that are sparse by nature. Its geometry is suggestive enough to draw attention, yet delicate enough to be reshaped by statistical choices. Rotate the coordinate system, change the smoothing scale, alter how neighbors are defined. Sometimes the shape holds, sometimes it frays. This does not make the claim dishonest. It makes it unresolved, and unresolved claims are the most uncomfortable kind, too structured to ignore, too sensitive to trust blindly. Cosmology lives in this discomfort more often than headlines admit. The public story of science celebrates breakthroughs. The internal reality is quieter, teams checking each other's assumptions, rerunning analyses with different cuts, asking whether an effect survives when enthusiasm is removed from the equation. It is slow. It is tedious. It is how the field protects itself from its own excitement, because excitement is dangerous when scale is involved. At cosmic distances, your intuition has no calibration. Billion light-year structures do not feel different from 100 million light-year ones. Both sound impossibly large, without careful discipline. Everything extraordinary begins to feel equally plausible. Maps are where discipline is enforced. Every dot placed on a cosmic map carries uncertainty. Every line connecting them carries inference. And when those inferences begin to resemble symbols, rings, arcs, walls, the first response is not awe, it is suspicion. Is the pattern aligned with survey edges? Does it persist across independent data sets? Does it survive when assumptions are relaxed rather than tightened? These questions do not kill discovery. They decide whether discovery deserves survival. Mapping the sky with imperfect eyes teaches you a humbling lesson. The universe is not obliged to present itself cleanly. If it appears clean, you should ask why. Not because nature is deceptive, because tools are. And yet, despite all this, cosmic maps work astonishingly well. They predict gravitational lensing patterns. They reproduce the cosmic microwave background statistics. They forecast where galaxies cluster and where voids open. Imperfect tools, used carefully, converge on a consistent story. That consistency is the reason anomalies matter at all. If everything were chaos, nothing would stand out. It is precisely because the universe behaves so regularly that irregularities become meaningful. The ring draws attention not because cosmology is sloppy, but because it is usually precise, and precision sharpens doubt. You are not looking at a photograph of reality. You are looking at reality filtered through design, necessity, and restraint. Maps do not show you the universe as it is. They show you the universe as it can be known. The difference is subtle, and at the largest scales, it becomes decisive. No survey is neutral. Every telescope edits reality by what it can see, when it looks, and what it ignores. The map feels objective until you notice the fingerprints. At some point, coincidence stops feeling accidental, not because it proves anything, but because it demands attention. In cosmology, attention is expensive. It is earned only when a pattern survives boredom, skepticism, and repetition. The big ring and the giant arc earned attention not by shouting, but by lingering. They appear in roughly the same region of the distant universe. They trace similar epochs in cosmic time, and they raise the same uncomfortable question from two different angles. Are we looking at structure or at ourselves? The Big Ring is not a solid object. It is not a halo of matter you could fly around. It is an alignment inferred from how distant gas absorbs light from background quasars. When those absorption signals are plotted in space, they outline a broad B, curved arrangement, suggestive enough to resemble a ring when viewed from our vantage point. The giant arc tells a similar story, but with a different accent. It appears as a sweeping curve of correlated material, extended across distances that rival the largest known cosmic structures, not dense enough to stand out as a cluster, not random enough to fade into noise. It occupies an uncomfortable middle ground. Individually, either claim could be waved away. Together, they resist that instinct, because if the universe were merely playing statistical tricks, you would expect anomalies to scatter randomly across space and time. One here, one there. Not too massive. Coherent features emerging from neighboring cosmic neighborhoods, shaped differently but pointing to the same tension. That tension is not about existence. It is about organization. The universe is allowed to be lumpy. It is allowed to produce filaments longer than intuition can tolerate. It is allowed to surprise you with scale. What unsettles cosmologists is not size alone. It is shape with persistence. Rings and arcs imply coordination. They suggest that matter didn't just gather, it arranged. And arrangement implies history. But whose history? If these features are real, they hint at correlations imprinted early, before the universe had time to smooth itself out. They would suggest that the primordial conditions, the faint fluctuations seeded during inflation, carried structure farther than expected. That gravity amplified those imprints without shredding them into statistical anonymity. That is a big claim. Alternatively, the history might not belong to the universe at all. It might belong to the surveys that observed it. Large-scale surveys do not sample space uniformly. They scan where telescopes can look, where dust allows, where instruments perform best. Quasars are not evenly distributed. Absorption systems appear only when conditions align. The data that traces these features is sparse by design. Sparse data is vulnerable. When you connect sparse points, the lines you draw matter. Change the criteria for what counts as connected, and shapes morph. A ring becomes an arc. An arc becomes fragments. Fragments dissolve into background. This is not manipulation. It is sensitivity. The big ring and the giant arc sit near the edge of that sensitivity. Their appearance depends on how aggressively you group signals, how you define neighborhoods in a space that is not directly observable. But here is what keeps them from being dismissed outright. They are not single pixel illusions. They involve hundreds of measurements spread across enormous volumes. They persist under multiple reasonable analysis choices. They do not vanish the moment scrutiny begins. They weaken. They shift. But they do not simply disappear. This is where the story becomes uncomfortable for both believers and skeptics. Believers want coherence, a clean, undeniable structure that forces theory to adapt. Skeptics want fragility, a pattern that collapses under minimal pressure. What they get instead is ambiguity. Ambiguity is not failure. It is friction. The big ring and the giant arc create friction because they live exactly where cosmology's assumptions are thinnest, at scales so vast that intuition fails, and methodology becomes destiny. At those scales, you are not asking whether gravity works. You are asking whether your way of counting works. That distinction matters. If these structures are artifacts, they teach you about bias, selection, and the psychology of pattern recognition in big data. They show how easily scale can amplify coincidence into apparent meaning. If they are real, they teach you something more unsettling, that the universe retains memory at scales where you assumed forgetfulness. Both lessons are valuable. Both are humbling. Notice what is absent from this debate. There is no rush to explanation, no immediate invocation of exotic physics, no confident declaration that cosmology is broken. That restraint is not timidity, it is maturity. Because cosmology has learned, painfully, that extraordinary patterns often fade with better context. The history of the field is littered with claims that felt inevitable at the time and trivial in hindsight. And yet some did not fade. Some survived replication. Some forced new parameters into models. Some rewrote textbooks. At the moment, the big ring and the giant arc exist in that narrow corridor between noise and necessity. They are not loud enough to demand revolution. They are not weak enough to be ignored. And that is precisely why they matter. They force cosmology to examine its own confidence, to ask whether smoothness is being tested or merely assumed, to confront the possibility that large-scale coherence might be rarer but not forbidden. You might feel a temptation to choose a side, to decide whether these structures are real or illusory. That instinct is understandable. Stories crave resolution. But cosmology does not move at the speed of stories. It moves at the speed of verification. Independent data sets must weigh in. Different traces must be consulted. Alternative analyses must try and fail to erase the pattern. Only then does a structure earn the right to be considered part of the universe's architecture. Until then, the big ring and the giant arc remain provisional. Not in the sense of being flimsy, but in the sense of being unfinalized. They are questions, not answers. Two immense shapes, same era, same sky, same unease. Coincidence starts to feel like a word doing too much work. Patterns feel meaningful because your brain was built to find them. Long before telescopes and datasets, pattern recognition kept you alive. You learned to spot faces in shadows, movement in tall grass, rhythm in chaos. Missing a pattern was costly. Seeing one where none existed was usually harmless. That instinct never turned off. It only scaled up. Now, instead of grass and predators, you face millions of data points scattered across cosmic distances, and the same machinery goes to work, searching for coherence, alignment, repetition. When it finds something, especially something large, it feels profound. But the universe does not care how convincing a pattern looks. In cosmology, noise is not the absence of information. It is information behaving randomly, and random processes, when sampled enough times, produce extremes, clusters, voids, apparent structure. The larger the data set, the more dramatic those extremes can become. This is not a flaw, it is mathematics. Imagine flipping a coin a few times. Heads and tails alternate. Nothing remarkable. Flip it 1,000,000 times, and somewhere you will find a long streak, hundreds of heads in a row. That streak feels intentional. It isn't. It's inevitable. Cosmic surveys operate on the same principle. When you map the universe with millions of tracer galaxies, quasars, absorption systems, you are guaranteed to find alignments that feel too organized to be chance. Some of them will be, most will not. The challenge is that chance does not announce itself as chance. Noise does not look noisy when it clusters. It looks purposeful, especially when filtered, smoothed, and visualized in ways your brain prefers. This is where the danger lies. Cosmologists do not observe raw randomness. They process it, they bin it, they correlate it. They project it into 3 dimensions using models of expansion. Each step clarifies and each step reshapes. Noise, under enough transformation, can acquire geometry. A subtle overdensity becomes a filament. Several filaments appear to curve. A curve suggests an arc. An arc, extended far enough, hints at a ring. None of this requires deception. It requires selection. Which points are considered neighbors? What distance threshold connects them? How much smoothing is applied? What happens at survey boundaries? These choices are not arbitrary, but they are consequential. Change them slightly, and patterns breathe expanding, contracting, sometimes dissolving. This sensitivity is not a sign of weakness. It is a signal that you are operating near the limits of inference. In statistics, there is a concept known as the look elsewhere effect. It describes a simple truth. The more places you search, the more likely you are to find something unusual somewhere. Not because it is meaningful, but because rarity becomes common when opportunities are vast. The sky offers endless opportunities. If you scan enough cosmic volume with enough parameters, a structure will eventually look exceptional. The mistake is treating that exception as proof rather than invitation. An invitation to ask, exceptional relative to what? To simulations? To randomized catalogs? To expectations defined before seeing the data? Or to expectations adjusted afterward, once the pattern already felt compelling? That last distinction matters more than it seems. Patterns discovered after extensive searching are vulnerable to overestimation. They feel significant because they survived selection, but selection was guided by curiosity, not by blind testing. The universe did not nominate the pattern. You did. This is why cosmology is wary of beauty. Beauty is persuasive. Symmetry seduces. Coherence invites narrative. But the universe is under no obligation to present itself in forms pleasing to human intuition. Noise, when left alone, is ugly. When interpreted, it can become elegant, and elegance is dangerous. The Big Ring and the giant arc sit precisely at this intersection. Their geometry is compelling enough to feel intentional. Their statistical support is strong enough to resist immediate dismissal. Their sensitivity to analysis choices keeps them from certainty. They are not ghosts. They are not monuments. They are tests. Tests of whether pattern recognition has outrun restraint. Cosmologists know this risk well. That is why extraordinary claims are subjected not to admiration, but to boredom. A pattern must survive being reanalyzed by people who want nothing from it. People with no emotional investment. People actively trying to make it disappear. Most patterns do disappear. That does not make the search futile. It makes the survivors meaningful. When a structure persists across traces, across surveys, across methodologies, it earns credibility slowly. It becomes part of the cosmic narrative not because it is dramatic, but because it is stubborn. Noise cannot do that. Bias can try. Only reality can persist. This is why the question surrounding these structures is not emotional. It is procedural. Does the pattern survive randomization? Does it appear in mock universes with similar selection effects? Does it re-emerge when the analysis is blinded? Each yes adds weight. Each no peels it away. And here is the quiet truth that often goes unsaid. Even when a pattern is noise, discovering why it appeared is valuable. It teaches you about your tools, your assumptions, and your blind spots. False patterns are not failures, they are diagnostics. They show you where your intuition is strongest and where it betrays you. The universe is not obligated to be legible. You impose legibility through models, averages, and patience. Noise is the price you pay for scale. The larger the canvas, the more tempting it becomes to read meaning into texture. And yet, without that temptation, nothing would be discovered at all. Progress lives in the tension between curiosity and restraint, between seeing something and insisting it survive doubt, between wonder and discipline. The Big Ring and the giant arc exist in that tension. They are not proof that the universe is whispering secrets. They are reminders that you are listening through imperfect filters. The human mind will always see patterns first. Science exists to ask whether those patterns deserve belief. The danger is not seeing patterns. The danger is falling in love with them too quickly. The human mind is a machine built for meaning. Give it enough data, and it will always find something to hold on to. The danger is not seeing patterns, it's believing every one of them deserves faith. This is where wonder is set aside. Not abandoned, set aside so it doesn't interfere with judgment. In cosmology, every extraordinary pattern must pass through a place that feels almost judicial, a space governed not by excitement, but by probability, not by how compelling something looks, but by how unlikely it truly is. This is the statistics trial. The charge is simple. Is this structure a signal, or is it an illusion? The verdict is anything but. In everyday life, probability feels intuitive. You flip a coin, roll a die, draw a card. Outcomes feel discrete, fair, contained. But cosmology deals in continuous spaces and enormous sample sizes. Here, probability behaves differently. Rare events stop being rare. Extremes become expected. This is where many cosmic claims stumble, not because they are wrong, but because they are misjudged. Consider significance. A pattern may appear unlikely in isolation, say, a 1 in 1,000 event. That sounds impressive, but if you effectively ran thousands of tests across the sky, trying many scales, shapes, thresholds, then 1 in 1,000 is no longer surprising. It is inevitable. This is known as the look elsewhere problem, and it is ruthless. It does not ask whether a pattern looks special. It asks how many chances you gave the universe to surprise you. Every adjustment counts. Every way of slicing the data counts. Every decision made after seeing the result counts. The more freedom you allow, the higher the burden of proof becomes. In this trial, intention does not matter. Only accounting does. Cosmologists respond to this with discipline. They generate mock universes, simulated skies that obey known physics, but contain no special structures by design. They run the same analysis pipelines on these mocks that they run on real data. They ask a brutal question. How often does something this impressive appear by accident? Sometimes the answer is reassuring. Sometimes it is uncomfortable. A pattern that seemed extraordinary may appear routinely in randomized universes, once selection effects are included. A structure that looked unique may dissolve into statistical normality when the correct penalties are applied. And yet, not everything dissolves. Some patterns remain rare even after every known correction. They persist across reasonable methodological choices. They resist erasure. These are the cases that keep cosmologists awake. The big ring and the giant arc sit on that knife edge. Their reported significance is not trivial, but neither is it overwhelming. Depending on how conservatively you account for look elsewhere effects, their statistical weight shifts. Strong enough to notice, weak enough to doubt. This is not indecision, it is honesty. Statistics does not tell you what is real. It tells you how surprised you should be if something were not real. And surprise is a fragile currency. The universe is vast. Data is messy. Models are imperfect. Under these conditions, demanding absolute certainty is unreasonable. But relaxing standards too far invites self-deception. So cosmology errs on the side of restraint. The trial is not a single calculation. It is a process. Reanalysis by independent teams. Different traces, different assumptions, different codes. The goal is not consensus, it is convergence. When independent approaches begin to point in the same direction, confidence grows. When they diverge, doubt deepens. The uncomfortable truth is that some questions remain suspended for years, even decades, because data is insufficient to convict or acquit. This limbo frustrates outsiders. It feels like hesitation, like fear of bold conclusions. In reality, it is the cost of scale. At these distances, error bars are not nuisances. They are dominant features. They shape interpretation more than signal does. A ring that spans billions of light years does not just challenge theory. It challenges methodology. It forces statisticians to confront whether their tools are calibrated for extremes or merely adequate for averages. And here, averages are deceptive. Most cosmological tests are optimized for global behavior. They excel at measuring expansion rates, matter, density, background smoothness. They are less sensitive to rare configurations. When a rare configuration appears, it pushes tools beyond their comfort zone. This is where judgment matters. Is the pattern robust to reasonable skepticism, or does it survive only under favorable assumptions? That distinction defines the outcome of the trial. The Big Ring and the giant arc have not failed this trial, but they have not passed it either. They remain under review, neither dismissed nor canonized. And that unresolved status is telling. It tells you that the evidence is intriguing but incomplete, that the universe may be whispering something subtle, or that your instruments are amplifying coincidence. Both possibilities demand patience. This patience is not passive. While the verdict waits, cosmologists refine methods, expand surveys, and design analyses that reduce freedom. They seek ways to ask questions that cannot be retrofitted to match desired outcomes. They do this because history is unforgiving. Past anomalies that vanished taught humility. Past anomalies that survived taught progress. The difference was not enthusiasm, it was endurance. Statistics does not reward cleverness. It rewards survival under pressure. So the trial continues, not in headlines, but in spreadsheets, not in declarations, but in footnotes, quietly, methodically. Without drama, this is where cosmology earns its credibility, not by being right immediately, but by refusing to be wrong loudly. In the end, the statistics trial is not about the universe, it is about discipline. Discipline to accept uncertainty. Discipline to resist narrative too early. Discipline to let probability, not preference, decide whether the Big Ring and the giant arc are signals or illusions. They have already served a purpose. They have forced cosmology to slow down, to sharpen its tools, and to remember that scale magnifies not only wonder but error. Here, excitement meets discipline. Every claim stands cross-examined by probability, bias, and repetition. Not because science distrusts discovery, but because it distrusts itself first. Suppose it survives, not the headlines,
This pattern,
not
this
the first
repetition,
wave of skepticism,
it violates
but
the
years of
cosmological
reanalysis,
principle.
independent data sets, alternative traces, harsher statistics. Suppose the Big Ring, or something meaningfully like it, refuses to disappear. At that point, the question changes. It is no longer, did we make a mistake? It becomes, what did the universe remember that we assumed it would forget? Because if the structure is real, then size is not the only issue. Persistence is. The universe was supposed to smooth itself out. Early fluctuations, tiny differences in density left over from the first moments after the Big Bang, were meant to grow into galaxies and clusters, then blur into statistical sameness at the larger scales. That expectation is woven into every modern cosmological model. A coherent structure spanning billions of light years would mean that expectation is incomplete, not wrong, incomplete. It would suggest that the early universe imprinted correlations stronger, longer lasting, or more spatially connected than our current models predict. That the seeds planted at the beginning did not merely grow, they coordinated. This does not require exotic forces or science fiction. The most unsettling possibility is also the most conservative, that known physics, under extreme conditions, produced outcomes we underestimated. Inflation, for example, is usually treated as a mechanism that smooths and randomizes. But inflation is not a single theory. It is a family of models. Some allow for subtle anisotropies, Some allow for long-range correlations that do not vanish neatly. If the universe inflated in a slightly uneven way, those imperfections could stretch across cosmic time. Gravity, too, may play a quieter role than expected. In simulations, structure formation often fragments at large scales. But simulations are simplifications. They trade resolution for scope. They average over processes that may matter more than assumed. A real, ring-like structure would not scream, "new physics." If you caught first, it would whisper, "missed nuance." Imere and nuance is where revolutions begin. If such coherence exists, it would not overthrow the cosmological principle outright. Instead, it would force a refinement. Smoothness would become contextual rather than absolute. Homogeneity would be statistical, but with tails rare. Extreme deviations that matter precisely because they are rare. Cosmology already lives with this idea in other domains. Dark matter behaves simply in bulk, but produces complex local behavior. Dark energy appears uniform, but drives radically different futures depending on small parameter shifts. A real structure at this scale would extend that lesson to geometry itself. It would mean the universe is not just lumpy, but occasionally coordinated. This has consequences. Distances inferred under the assumption of perfect large-scale smoothness might need recalibration in regions influenced by such structures. Expansion measurements could acquire subtle directional dependencies. Cosmic variance, already a limiting factor, would grow teeth. The universe would still be comprehensible, but it would be less forgiving. And then there is the philosophical weight. A real big ring would remind you that cosmology is not a closed book, that even the largest assumptions, those that feel foundational, are provisional, that the universe does not owe simplicity to understanding. This is not failure, it is vitality. Science stagnates when its core assumptions stop being tested. It advances when anomalies survive long enough to demand accommodation rather than dismissal. But survival comes with responsibility. If the structure is real, it must be integrated carefully, not sensationalized, not used as proof that everything we know is wrong. That phrase has ended more serious inquiry than it has ever helped. Instead, the right response would be measured curiosity. How common are such structures? Are they confined to specific epochs? Do they correlate with known features of the early universe? Can simulations reproduce them without tuning? Each question opens a new chapter, not a collapse. And there is a deeper implication that is easy to miss. A universe capable of sustaining coherence across billions of light years is a universe with memory, not consciousness, not intention, but causal continuity that resists erasure. That idea shifts how you think about cosmic history. It suggests that the earliest moments did not merely set initial conditions, they set relationships that survived expansion, chaos, and time. You are not just living in a universe that grew, you are living in one that remembers. That memory does not privilege you. It does not point to meaning or purpose, but it reframes scale. It tells you that distance does not always dilute significance. In such a universe, rarity matters, extremes matter. Outliers matter not because they dominate, but because they reveal the limits of expectation. If the big ring is real, then the universe has quietly informed you that its largest structures are not just statistical leftovers. They are messages from its earliest state, stretched thin but not erased. And that realization demands humility of a different kind. Not the humility of insignificance, but the humility of incomplete understanding. You would still be small. The universe would still be vast. But the relationship between them would feel less mechanical and more contingent. The cosmos would no longer be just a smooth backdrop punctuated by accidents. It would be a system capable of rare, persistent coherence, unpredictable, subtle, and difficult to map. And difficulty is where knowledge deepens. If the structure is real, Cosmology does not collapse. It matures. It learns where its approximations break down. It discovers where its confidence was borrowed rather than earned. And it gains a new set of questions powerful enough to justify decades of work. Reality would still work, just less comfortably. Then the task would be clear. Not to celebrate the anomaly, but to understand it without turning it into myth. Because the universe does not reward certainty. It rewards those willing to follow evidence into discomfort and stay there long enough to learn. Then the universe is not as smooth as we believed. And the rules we leaned on were approximations, not foundations. Reality would still work, just less comfortably. Suppose it fades, not dramatically, not with an apology or a retraction headline. It simply weakens under scrutiny, loses coherence when assumptions change, fractures when datasets expand, dissolves when methods harden. No ring, no arc, no forbidden structure. At first, this outcome feels disappointing. A letdown after all that scale, tension, and anticipation. But in cosmology, disappearance is not failure. It is instruction, because when a structure is not real, the universe has still taught you something essential, just not about itself. It has taught you about how easily meaning can emerge from noise. Big data sets invite big illusions. When you work with millions of points across billions of light years, coincidence doesn't look random anymore. It starts to resemble design. Curves appear. Alignments form. Boundaries masquerade as features. This does not mean the scientists involved were careless. Quite the opposite. It means they were operating at the frontier where inference becomes fragile. If the big ring is not real, then its temporary plausibility reveals how sensitive cosmology is to its own tools. It shows how quickly scale amplifies bias, how readily geometry emerges from sampling. And that lesson matters more than any single structure, because modern cosmology is no longer data-starved. It is interpretation-limited. Telescopes grow faster than intuition. Surveys outpace theory. The bottleneck is no longer observation, it is judgment, deciding which patterns deserve belief, and which are artifacts of how the sky was sliced. A false structure does not indict cosmology. It refines it. It forces the field to confront the look elsewhere effect in practice, not just in textbooks. It exposes where statistical penalties were underestimated. It reveals which visualization choices seduced interpretation. In this sense, a vanishing structure is not erased. It is absorbed into methodology. The history of science is full of such ghosts. Apparent canals on Mars, steady-state cosmology, faster than light neutrinos. Each illusion sharpened the tools that replaced it. Cosmology advances not just by discovering what exists, but by learning what cannot be trusted. If the big ring is not real, then the most important outcome is not relief. It is recalibration. How many patterns should you expect to see by chance in a dataset this large? How should significance be defined when the sky itself offers endless degrees of freedom? When does exploration become fishing? These are not abstract concerns. They shape how future discoveries will be evaluated. They determine whether the next anomaly is embraced, ignored, or dismantled correctly. There is also a human lesson here, one that reaches beyond science. You are uncomfortable with the idea that something so compelling could be illusory because your brain equates scale with importance. Something that large feels like it must matter, but the universe is under no obligation to match that instinct. Noise does not scale gently. It scales brutally, given enough space. Randomness will eventually produce something that looks intentional. The danger lies not in randomness, but in forgetting how powerful it becomes at size. If the structure is not real, then the universe has not betrayed you. Your expectations betrayed you, and recognizing that is progress. It takes maturity to accept that a beautiful idea does not survive contact with better analysis. It takes discipline to let go of a pattern that once felt meaningful. It takes courage to publish null results when narratives would prefer certainty. Science depends on that courage. There is also a quieter implication. If the big ring is not real, then the cosmological principle emerges not as fragile dogma, but as resilient approximation, not perfect, not eternal, but sturdy enough to survive provocation. That survival matters. It means distances remain interpretable. Expansion remains global. Cosmic history remains coherent. The universe stays readable not because it is simple, but because its complexity averages out as expected, smoothness. In this outcome is not disproven. It is reaffirmed under pressure, and that affirmation is not boring. It is stabilizing. It tells you that the universe behaves predictably enough to be understood without resorting to mythology, that its largest features emerge from simple rules applied consistently, rather than from rare exceptions that dominate interpretation. But do not mistake this for closure. A false structure does not end curiosity. It redirects it. Why did this pattern appear here and not elsewhere? What specific combination of data sparsity, survey geometry, and human intuition gave it form? What other illusions are waiting to be mistaken for insight? These questions sharpen future exploration. They make cosmology more cautious, not more timid, more skeptical, not more cynical, more reliable, not less ambitious. The absence of a structure is still a data point. It tells you something about the limits of correlation, about how structure fragments beyond certain scales, about where the universe genuinely becomes indifferent to shape, and indifference is informative. If the structure is not real, then the universe is telling you that it does not preserve coherence arbitrarily, that it erases memory efficiently at extreme distances. That large-scale uniformity is not an assumption clinging to relevance, but a pattern earned through endurance. That outcome does not diminish wonder. It deepens it, because it means the universe is not quietly conspiring to surprise you with hidden symbols. It is operating according to rules that, while subtle, are consistent. Consistency is not dull. It is what allows meaning to exist at all. A universe that behaved arbitrarily would be impossible to know. A universe that behaves reliably, but occasionally tempts you with illusion, invites humility. If the big ring is not real, then the real story is not about a missing structure. It is about restraint winning over excitement, about science choosing patience over spectacle, and that choice is not a loss. It is how knowledge stays intact. Then the lesson is quieter, but no less important. It tells you how easily scale and randomness can imitate intention, and how restraint can be as valuable as revelation. You never see the universe whole, no matter how powerful your instruments become, no matter how far surveys extend. You inhabit only a fragment of the cosmic story. Light reaches you late. Information arrives filtered. Vast regions lie forever beyond your horizon, not hidden by distance alone, but by the expansion of space itself. This is not a technical inconvenience. It is a defining condition. Every cosmic map you build is incomplete by nature. It captures what has had time to reach you, what your instruments are sensitive enough to detect, and what your methods are capable of interpreting. The rest remains silent not because it is empty, but because it is inaccessible. And yet, from this partial view, you attempt something audacious. You try to understand the whole. Cosmology is an exercise in inference under constraint. You take a thin shell of observable reality and extrapolate outward. You assume that what you see nearby is representative of what lies farther away. You rely on symmetry, repetition, and consistency to fill in gaps you cannot cross. This is not arrogance, it is necessity. Without these assumptions, knowledge would never scale. You would be trapped in local truths, unable to speak meaningfully about the universe beyond your immediate surroundings. But necessity comes with consequences. Living inside a partial cosmic map means accepting that certainty is provisional, that every conclusion is conditional on what has been observed so far. That future data may not simply refine your picture, it may redraw its boundaries. This is where the Big Ring story finds its deeper meaning. Whether the structure proves real or illusory, it exposed a simple truth. Your map is not the territory. It is a best effort, built under constraints you did not choose. That realization can feel destabilizing. It challenges the comfort that comes from clean diagrams and smooth narratives. But it also offers clarity, because a partial map is not useless. It is powerful precisely because it acknowledges its limits. The danger lies not in incompleteness, but in forgetting it. When you forget that your map is partial, assumptions harden into beliefs, models become identities, anomalies feel like threats rather than invitations to learn. Cosmology has avoided this fate by remaining suspicious of itself. It does not treat the observable universe as a perfect sample. It quantifies cosmic variance, the expected difference between regions. It models uncertainty explicitly. It builds confidence intervals around ignorance. This is why a single structure, no matter how large, cannot overturn the field overnight. It must prove that it survives the constraints of partial knowledge. Living inside a partial map means learning to interpret absence carefully. When something does not appear beyond a certain scale, is it because it does not exist or because your instruments cannot detect it? When a pattern appears once, but not elsewhere, is it unique or a statistical fluke amplified by selection? These questions do not have clean answers. They require patience. They require repetition. They require the willingness to wait for confirmation that may never arrive. This waiting is not passive. It shapes how science behaves. Surveys are designed to be wider, not just deeper. Methods are stress-tested against simulated universes. Analyses are blinded to prevent expectation from steering outcome. Each step acknowledges the same fact. You are reasoning from an incomplete view, and yet something remarkable happens. Despite all this incompleteness, the universe reveals itself with consistency. Independent measurements converge. Different tracers tell compatible stories. The age of the universe, the rate of expansion, the distribution of matter all agree within narrow margins. This convergence does not eliminate uncertainty. It gives it structure. A partial map can still be coherent. It can still be predictive. It can still be wrong in specific places while being broadly reliable. That balance is fragile and precious. The Big Ring forced cosmology to confront where that balance lies. It reminded the field that large-scale conclusions rest on assumptions that must remain flexible, that the map works not because it is perfect, but because it is constantly revised. Living inside a partial cosmic map also reshapes how you see yourself. You are not an external observer. You are embedded in the system you are trying to describe. Your location, your epoch, your technological limits all influence what you can know. You do not observe the universe from nowhere. You observe it from here. That perspective matters. It means some questions may remain unanswered not because they are meaningless, but because they are unreachable. It means some structures may lie beyond confirmation. It means some debates may persist indefinitely. This is not a weakness of science. It is a feature of reality. The universe is not obligated to be fully legible to its contents. And yet, from within this partial view, you have learned astonishing things. You have traced the universe's expansion back nearly to its beginning. You have measured fluctuations imprinted when the cosmos was only hundreds of thousands of years old. You have mapped the scaffolding of matter across billions of light years. All of this was done without ever seeing the whole. That achievement deserves respect, not because it is complete, but because it is disciplined. The danger now is not that the map is partial. The danger is pretending it isn't. When anomalies arise, the correct response is not panic or denial. It is curiosity tempered by method, a willingness to ask whether the map needs refinement or whether the anomaly reflects the limits of perception. The Big Ring asked that question sharply. It did not demand an answer. It demanded humility. Living inside a partial cosmic map means accepting that your knowledge will always trail reality. That understanding grows asymptotically, never reaching completion. That certainty is not the goal coherence is, and coherence does not require perfection. It requires honesty about what is known, what is assumed, and what remains open. You do not see the universe directly, only through layers of method and meaning. Every map is incomplete, yet still useful. That tension is not a flaw. It is the price of knowing anything at all. The sky has not changed. What changes is how well you can interrogate it. For most of cosmological history, uncertainty did not come from disagreement. It came from absence. Not enough data, too few objects, gaps in coverage so large that speculation filled the silence. In that era, anomalies were easy to generate and impossible to resolve. That era is ending. Future telescopes do not promise answers. They promise resolution, and resolution is more demanding than mystery. When the Big Ring and the giant arc entered the conversation, they did so at the edge of what existing surveys could reliably probe. Sparse traces, uneven sky coverage, redshift uncertainties that blur structure into suggestion. These limitations did not invalidate the claims, but they constrained judgment. What future instruments change is not the universe, but the room it has to hide. New surveys will map larger volumes with greater uniformity. They will observe fainter objects, reducing reliance on rare traces. They will overlap sky regions intentionally, allowing independent confirmation rather than single survey authority. This matters because ambiguity thrives where data is thin. When coverage becomes continuous, patterns either strengthen or fracture. Coherence becomes harder to fake. Geometry becomes harder to impose. Structures must earn persistence across methods, not just survive within one. Future telescopes will not look for rings. They will remove excuses. They will reduce selection effects, not by correction, but by avoidance. Wider fields mean fewer edges. Deeper observations mean less bias toward luminous outliers. Better calibration means fewer hidden gradients masquerading as structure. This is how cosmology advances, not by chasing anomalies, but by closing loopholes. If the Big Ring is real, future data will not merely confirm it. It will contextualize it, show whether it is unique or part of a broader population, reveal whether its shape is intrinsic or a projection effect, determine whether it correlates with other large-scale features or stands alone. Uniqueness matters. A single coherent structure at extreme scale is intriguing. A population of them changes the narrative entirely. It would suggest that rare coherence is not an accident, but an allowed outcome under specific conditions. Future telescopes are designed to answer exactly that kind of question. They will also tighten statistical discipline. Larger datasets reduce the look elsewhere effect, not by eliminating it, but by quantifying it more honestly. When your sample grows, you can define rarity with precision rather than approximation. This does not guarantee clarity. It guarantees accountability. But there is another way future observations may decide the issue quietly, indirectly, without ever mentioning the Big Ring at all. By reinforcing consistency elsewhere, if new surveys continue to show large-scale smoothness with shrinking uncertainties, the space for extreme coherence narrows. The universe becomes more tightly constrained. Anomalies that once felt plausible become less so, not because they are disproven, but because they lack room to exist. This is how theories survive, not by confronting every anomaly head-on, but by becoming so predictive that anomalies struggle to breathe. Future telescopes also changed the psychology of discovery. When data was scarce, surprise felt precious. Now, surprise must justify itself. The burden shifts from "this looks strange" to "this survives every attempt to make it ordinary." I know, that shift favors patience over proclamation. It favors collaboration over ownership. It favors silence until confidence emerges. And confidence, in cosmology, is rarely loud. There is a temptation to imagine future telescopes as judges delivering verdicts. But they are not courts. They are mirrors. They reflect back the strengths and weaknesses of current assumptions with sharper clarity. They will not decide whether the universe is strange. They will decide how precisely it is strange. If the big ring fades under their gaze, the lesson will be methodological, a reminder that inference must evolve with scale. That pattern recognition must be matched with restraint, that the universe resists narrative simplicity. If it survives, the lesson will be deeper, a signal that early conditions carried more structure than anticipated. That smoothness is an approximation with rare exceptions. That cosmology must widen its conceptual tolerance. Either way, the outcome strengthens the field. This is the quiet confidence of modern cosmology. It does not fear being wrong. It fears being sloppy. Future telescopes embody that ethic. They are not built to confirm beliefs, but to pressure test them, and pressure reveals truth, not immediately, not cleanly, but persistently. There is also a human dimension to this future. The next generation of astronomers will inherit these questions without the emotional investment of their origin. They will approach the data without attachment to the initial excitement. That distance is valuable. It allows skepticism to function without hostility. Science progresses best when curiosity outlives ownership. The big ring may be remembered as a discovery, a mirage, or a footnote, but the infrastructure built to resolve it, the surveys, the methods, the discipline will shape cosmology, regardless of outcome. That is the deeper decision future telescopes make, not which anomalies survive, but which standards endure. The sky will continue to offer patterns. Some will be real, some will dissolve. The role of future instruments is not to eliminate mystery, but to sort it patiently, repeatedly, without drama. The universe does not rush, neither should understanding. The sky has not changed. Only our tools have, and with sharper eyes. Uncertainty does not vanish, it becomes more honest. At the end of this journey, nothing explodes. There is no final revelation. No cosmic curtain pulled back to reveal a hidden truth waiting just beyond the horizon. Instead, what remains is quieter and more demanding. You arrive at the edge of what can be known, and the universe does not offer closure. It offers perspective. Humility is not a moral gesture in cosmology. It is a working principle. Without it, the field collapses under its own ambition. With it, uncertainty becomes navigable rather than paralyzing. Every story you have followed about size, structure, smoothness, anomalies circles back to the same realization. The universe is larger than any framework you bring to it, not just in distance, but in possibility. Cosmology did not begin as a quest for wonder. It began as a need for order. Early astronomers wanted the sky to behave. They sought regularity in planetary motion, repetition in stellar cycles, predictability in the heavens. And for a long time, the universe rewarded that effort. It obeyed. But as measurements deepened and scales expanded, obedience gave way to complexity. Order did not vanish, it became conditional. Patterns emerged, but only when viewed correctly. Smoothness appeared, but only statistically. Certainty survived, but only with margins. Humility grew not because scientists lost confidence, but because confidence matured. The Big Ring story whether it ends as confirmation or correction, fits this arc perfectly. It is not a tale of discovery triumphant or illusion exposed. It is a demonstration of how knowledge behaves at its limits. At those limits, answers slow down, claims soften, language becomes careful. This is not weakness. It is calibration. The universe does not reward haste. You might be tempted to see humility as resignation, as an admission that some questions are simply too big. But cosmology has never retreated from big questions. It has only learned how to ask them without demanding immediate satisfaction. Humility is what allows you to hold two truths at once, that your models work remarkably well, and that they remain incomplete. This balance is fragile. Lean too far into confidence, and anomalies become threats. Lean too far into doubt, and structure dissolves into nihilism. Progress lives between these extremes. The edge of cosmic knowledge is not marked by ignorance. It is marked by restraint, restraint in interpretation, restraint in storytelling, restraint in declaring what the universe must be. This restraint does not diminish wonder. It protects it, because wonder built on certainty collapses the moment certainty fails. Wonder built on humility endures, adapting as understanding grows. You live in a universe where most of what exists will never be observed directly, where the majority of matter is invisible, where the majority of time lies ahead, not behind. Any attempt to master such a reality must begin with acceptance of limitation. That acceptance is not passive. It fuels innovation. It drives the construction of better instruments, sharper analyses, broader collaborations. It keeps curiosity alive without letting it harden into dogma. Humility is what allows cosmology to revise itself without shame. It is why assumptions are treated as tools rather than truths, why anomalies are interrogated rather than worshipped, why conclusions are framed as provisional, not permanent. This is not indecision. It is intellectual integrity. Standing at the edge of cosmic knowledge, you do not feel small because the universe dwarfs you. You feel small because understanding demands more care than intuition alone can provide. And that care is uniquely human. No star worries about its origin. No galaxy questions its structure. Only a species capable of reflection can recognize the limits of its own explanations. That recognition is not defeat. It is distinction. The universe does not ask you to solve it. It asks you to observe honestly, interpret cautiously, and remain open to revision. Humility keeps that contract intact. Whether the big ring endures or fades, the deeper lesson remains unchanged. Knowledge is not a collection of facts. It is a process shaped by uncertainty, discipline, and time. You are not finished understanding the universe. You never will be. But that incompleteness is not a flaw in the endeavor. It is the reason the endeavor continues at all. At the edge of cosmic knowledge, the most reliable structure is not a ring, a wall, or a web. It is the willingness to admit what you do not yet know and to keep looking anyway. In the end, the universe does not ask for certainty. It rewards patience, skepticism, and the courage to say, "We don't know." That humility may be the most reliable structure we have ever built.